Соколовский.
Is it good?
Okay. He's a good guy. He was my first student. First grade student.
Okay, that's why I want to use a solid.
Do you want me to send an email to you?
Maybe. Will there be a signal from on high when I should mic up? I guess I can just test this. Hello? Oh, there we go.
I have you muted right now, so you can put it on.
Okay, great. But I've turned it on. Is that good? Okay.
Were you at the That's what it says on your t-shirt.
And yes.
But where would you see it?
Somewhere in like North Carolina or something. I think North Carolina. Or it says where it was. Oh no, it was Tennessee.
Tennessee?
No, it was in the path of totality.
Yeah. Madisonville, Tennessee, according to the shirt.
Yeah, okay, that must have been the last point in the U.S. where you could see it, or close. Because Tennessee is not on the coast. So
Right, but I think Carolina was
I know, because we saw it in the Oregon coast. So we were like right on the coast. At the very, very beginning of the totality. I guess if you were on a boat, you could have seen it. Was it like amazing?
Of course, yeah. I mean, was it a region for in Oregon as well?
Oh, it's like, I've seen like one before when I was just like when I was 13. And everyone's like chatting, and it's like, oh, whatever. And then when you could have heard the intro. Like everybody was like, oh my god, like something is blocking out the sun. And that was just like, this is really happening. And everybody just gets quiet. And it was a full 2 minutes totality. And it was very magical. Like a second before, the kids were like screaming and everyone was like, this weird light comes on, all the roosters start going to bed. Were you normally in Texas, or you drove there just to be?
Drove there. I drove like 10 hours just to be. Yeah.
Oh wow.
Yeah. There's one more. Is it like 2 years or so? I don't remember.
Next year, there's one in 2024. I don't know, I just find, I only did this because of my family. So, knowing that it was both going to be at the right time, then we just rented the house. But I'm not sure if I would drive 2 hours. So you're more of a diehard.
I'm not sure if I would do 10 hours again, but I think it's closer. So I would go like somewhere down.
I saw her. She was at the VHI. Yeah, I'll text her. I'll text her.
It's also so nice that I just sit there and stay stressed and probably get Let me just say it like louder.
I was gonna say she's
Say it louder. It's so nice to have that.
Yeah, exactly. Well, I'm having fun.
I'll sit there. I'll sit there. Yeah. I know. It was one of the reasons why I didn't buy them. Because
Cheers.
I just know how to design it.
bad.
Oh, maybe you know how you see pictures of
Fans are arriving.
Oh, I see.
Yeah, it's a different aspect.
All right, we're going to get started. I think Michael has some opening words. No pressure. Okay, well, thank you all for coming to Daniel Palumbo's PhD defense. I still vividly remember my first time meeting Daniel. This was actually in April of 2017. And Daniel was a junior at MIT, and he was doing experimental physics research. He was designing scintillating detectors for the dark light experiment. And he'd written to Shep and said he was extraordinarily interested in the EHT. So we invited him to come by the DHI, the Black Hole Initiative, and talk about it. So he came in, and Shep and I had just stepped out of an EHT go, no-go call. So this is a call where we look at the weather across all the stations in the EHT and technical readiness and try to decide whether or not we want to trigger observations for that night. And Daniel, he just bounded in. He was glowing with energy and enthusiasm. It was clear he was a really special student, and we hired him almost immediately. And we started off on a project to study what would happen if we could add space telescopes to the EHT. So that day turned out to be one of the most important days for any of us, although we didn't know it at the time. So it turns out that that night of observations led to the first ever images of a black hole, both for M87 and Sgr A, and it just was chance that Daniel was there. And I think this is really emblematic of Daniel. He's someone who always seems to be at the center of the most exciting events, and he's always working on the bleeding edge of what's possible. So since that first meeting, Daniel's been at the heart of every EHT result published to date. And he's usually working on the hardest open problem. He started off with simulations and imaging, and so he was working on turning EHT data into pictures. And he wrote the software that sifted through the multitude of images that are all consistent with EHT data to select one that was a representative average image, and then also to quantify the uncertainty associated with that. And then shortly after the EHT results were published in 2019, Daniel became interested in the question of what we could learn about black holes from polarized images. So for those who don't know, interferometry is already a pretty technical topic, especially when the sources you're studying are in a strongly curved spacetime. And moving to study polarimetric interferometry is like learning it all again, but in a new language that only 10 people speak. So this is something that Daniel's going to tell more about in his defense, but I just want to emphasize how central Daniel's work was to the EHT results. So when the EHT published the first polarization images of a black hole, in the accompanying theory paper, this metric that Daniel developed is referenced 89 times. So that's actually extraordinary. These are results that usually take years for a community to slowly assimilate and come to terms with. And Daniel's results were accepted almost immediately and were really central to the EHT findings. So since then, Daniel has turned his attention towards increasingly direct probes of a black hole spacetime. And his research is shaping how we interpret observations of black holes today. And I think when we look back a decade from now, we'll find that Daniel laid the path for some of the most exciting results that are yet to come. So Daniel is dedicated, he's fearless, and he's constantly surprising me with new skills and insights. One of the most surprising and wonderful memories I have is the first time I got to see Daniel play the virtual reality game Beat Saber. So to use a word from Shep, this was revelatory. I'm sorry, you probably won't get to experience that as part of this formal defense. But more seriously, Daniel really constantly energizes and elevates the experience of everyone around him. In addition to Beat Saber, his teaching skills are legendary, matched perhaps only by his baking. And I have no idea where he finds the time for all of these activities and passions. In addition to his prolific research output, he is also leading the MGHT subgroup on photon rings and also on ethical citing. And in addition to that, he's a very active member of the EHT Junior Scientist Council, which he's been on since he was elected as one of the inaugural members. So Daniel is tackling some of the deepest problems in astronomy by creating an entirely new set of tools and mapping the course for the next generation of groundbreaking experiments. You're in for a real treat today, and with that, I'm delighted to hand things over to Mr. Daniel Palumbo.
Oh my goodness. Oh my goodness. Okay, it sounds like the mic is working. Let me get my timer going, because otherwise I could talk forever. Michael, thank you so much for an incredibly generous and kind introduction. And it also means I don't need to repeat the same anecdote about how I joined, because you told it far better than I would. Yeah, so I am delighted to be here to share with you all a little bit about what I did as part of my PhD research from my thesis, Interferometric Measurement of the Magnetization and Spin of Supermassive Black Holes. I'm sure I don't need to tell you that making a PhD takes a village. And so I'd like to start with my acknowledgements, which I just want to say out front are heavily abridged from the exhaustive acknowledgements in my thesis. And so just as a blanket statement, if you are here now listening to me, or you are far away listening to me, or you are somewhere far in the future listening to a recording, there's a very good chance you've had a formative part in the joy and success of the PhD that I am here to defend. And I cherish all of you. So thank you all for being here. But more specifically, I would love to thank my advisor, Michael Johnson. I could easily fill this entire hour singing Michael's praises, and I often do precisely that whenever any student is considering joining our group, or just joining the CFA, or just walking by. And I'm sure a lot of people in this room feel the same way. Michael is just an absolute treasure to the EHT, to the local group, and it's a great honor to be his first graduate student that he's primary advising, and that's an honor I'll take with me forever. So Michael, thank you for everything. I also want to thank my committee, Ramesh Narayan, Jim Moran, and Shep Doleman. I had the great joy of teaching for Ramesh before I started co-authoring theory works with Ramesh of relevance to EHT work, which have been a big part in the tapestry of understanding polarization that I'll be talking about. And I learned something new from him and his research group meetings every week. It's a delight to bounce ideas off of him and just the wonderful collection of wisdom that he and his, the people he surrounds himself with. It's just a wonderful environment in which to learn and grow as a theorist. I also, of course, want to thank Jim Moran, without whom none of us would know how to do VLBI. And it's thanks to Jim's devout stewardship of this technique and its history that we know our role, really, in the history of radio astronomy and just how to do Fourier transforms with the right sign conventions. And of course, I want to thank Shep, who, as Michael mentioned, is the one who answered a cold email from a random MIT undergrad in the middle of the observations that would become the images that we know and love, and somehow found time to sit down with Michael and with me, and the rest is history. So Shep, it's been quite the ride, and I look forward to many more years of collaboration. I also want to give my profound thanks to Priya Natarajan, who is joining as my external examiner, joining us from Yale. Priya brings some incredibly important expertise on subjects that I have great enthusiasm but little knowledge in, specifically relating to the growth of black holes over cosmic time. It's what I consider to be the most compelling future application of the work that I'm going to outline to you all. And so it's imperative that Priya was able to join. And somehow on top of that, Priya is just an immensely energizing mentor and colleague. So Priya, thank you so much for being here. I also want to thank Peter Gallison, and by extension the BHI, the Black Hole Initiative, which is a wonderful interdisciplinary environment in which to grow as a scholar. I can't recommend it enough. It has, well, really, this is a lot of Peter's personal sort of endeavor to make EHT science, or to embed it in a more holistic and humanist view of how we present our results, of how we think about the science that we're doing. And it was also Peter who led me to my work with the Responsible Sighting Working Group of the Next Generation Event Horizon Telescope, thinking about the ethics and history and sociology of building, or whether or not to build, telescopes to expand, in this case, the EHT, which is some of the most fulfilling work that I do. So Peter, thank you so much. and thank you for being here today. I want to give a general thank you to the Event Horizon Telescope and my beloved colleagues and co-authors in this global collaboration, but of course the tens of you who are in the room right now. It is the great joy of my daily work that I get to interact with such lovely people. And this just the local mini-building, multi-institute conglomerate of all of us somehow happen to be just the most cozy research environment I've ever operated in. And this extends to the entire CFA community. This has been a delightful place to be a grad student, but especially I want to thank Peg Herlihy, without whom today simply just would not have occurred. So Peg is a treasure, and the rest of you are pretty cool too. And I want to thank my parents, Lynn and Dennis, who are watching from home. They've been unconditionally loving and supportive my entire life, which is basically all you can ask for. So great job, you guys. I love you to pieces, and I hope you enjoy the next 40-ish minutes. And last but certainly not least, I want to thank my beloved partner, Linus, who has been with me since before my PhD began, so you can tell he's had bad judgment for a really long time. But it's thanks to him that this is all possible, and I've dedicated my thesis to Linus because I hope you all get a chance to chat with him afterwards. Mostly I just want to inflict as much suffering on Linus as possible, but he's just a wonderful human being, and I love you, Linus. All right. So without further ado, it's at this point you should see a striking, inarguable resemblance between the French crullers that you've been eating for the last 10 minutes and the image on the left. So these two images are sort of the crowning achievements of the Event Horizon Telescope so far. On the left, we have the polarized image of Messier 87's supermassive black hole. So this is a giant elliptical galaxy in the northern sky, and we've taken a polarized image, and I'm showing this polarization with sugary glaze. Sorry, I mean white tick marks, where each of these little ticks, for those unfamiliar with this style of visualization, are indicating the orientation on the sky of the evolution of a light wave in the vicinity of that little tick mark. And on the right, this is the image of the Galactic Center, and you'll notice the absence of tick marks indicating this result is yet to come, but it's imminent. The majority of this talk will be talking about the polarization of Messier 87 because it's already published. And it was the motivation for a lot of the work that I did in sort of the middle years of my PhD. And much of what we've learned has to do with comparing images like these to simulations. And what remains to be learned, I will argue in this talk, also is intimately tied to what we can learn from accretion theory and from simulations of accretion in low luminosity active galactic nuclei. One of the big things we've learned is that if you have general relativistic magneto-hydrodynamical simulations, GRMHD, and you can, given a certain mass, produce images that you think represent what these look like at 230 gigahertz, where the EHD is observing, you can build a calibration from simulations with known mass to the blurry rings on the sky that we see, because the mass is mostly serving to scale the entire problem in and out on the sky. And so when we do this calibration, we can infer masses for our sources, and we tend to get things that are roughly consistent with other measurements, certainly within a factor of 2 for M87, and for Sgr we're basically dead on. And so that's a triumph for the experiment, but also just a triumph for our models, where they're doing something right if we're capable of getting this level of agreement. And we notice a preference in these model comparisons, especially in polarized model comparisons, for dynamically important magnetic fields in the accretion flow. And I'll be talking at great lengths about what I mean by this, but the general scheme here is that on the left we have the actual image of Messier 87 here emphasizing the polarized structure. And when we compare to the structure, the morphology of these little tick marks in simulations, we see a preference for one class of models over another, and there will be much ado about that. But the broad punchline is that our models resemble actual black holes. But we know that there are huge issues in the way we perform these simulations. We have to cut corners to make these feasible. We have to cut different corners to make them scalable. And we know we're doing plasma physics wrong. Every simulator who will ever come before you to give a talk, they'll be pouring their heart out with all of the corners they cut and all of the caveats. And so these caveats matter. They are intrinsic to the way we understand these sources in the sky. And so we know we aren't getting the full picture. And so we believe our results, our core claims, much more when simple arguments get the same answer. And so my thesis has largely focused on building tools, or experiments in some cases, that connect messy physics to fundamental physical properties of the system that we're interested in, things like the black hole mass, or, as I believe is most important, the black hole spin. And it's very fitting that the discussion at the end of Flora's defense this morning was on dirty physics, because really the through line of this talk is that it is inescapable. You will be dealing with messy astrophysics no matter what, so you might as well put it to work for you. Now, why do I think spin is so important? Well, this is an image of Messier 87 taken with Hubble. And in this image, you see a bright linear feature, which is a little washed out in this lighting, but you can see it sort of poking off to the northwest. And this feature, this bright line, is a jet of relativistically fast-moving charged particles coming towards us. And when you think of an accretion flow around a black hole, you expect a jet to be launched in both directions, but we only see one. And that's telling us that this jet is pointing towards us. It's being Doppler boosted towards us, and its partner, its counterjet, is being Doppler boosted away. And we infer from this jet an inclination around 17 degrees. And in our analysis of M87's inner accretion flow done with the EHT, we assume an inclination of something very close to that. We've by default used 17 degrees in our simulations. So why are we so confident in linking the inclination of something at this scale to the black hole accretion system? And the reason is because, to the best of our knowledge, to the best of all theory work done on this subject, the mechanism for launching these tightly collimated, powerful radio jets is something called the Blanford-Znayak mechanism, which directly extracts rotational energy from a rotating black hole and launches it into relativistically fast-moving jets. And so there is a linkage between these extraordinarily powerful features that we see across the universe and the very innermost scales. And it's all mediated by spin. In this case, it's mediated also by the magnetic field threading the black hole, and this will come back again in later discussions. And what's terribly exciting about measuring the spin is that we're not just constraining an important feedback mechanism, this jet, which turns out you need in order to explain why star formation rates are so low in so many galaxies. But the spin is also probing something about the history of the black hole. You might imagine that the supermassive black holes that surround us might have had a merger in which misaligned angular momenta joined to form a relatively slowly spinning black hole. Whereas if something has been accreting for a long time from a coherent source of a single direction of angular momentum, it might be more rapidly spinning. And so being able to measure spin probes not just the history and not just a feedback mechanism, but it also probes something that basically only we can measure in low luminosity active galactic nuclei. It is really tricky to get at these any other way. If you have something bright, or if you have an X-ray binary, you have hopes in X-rays, but these are not applicable to sources like Messier 87 and Sgr A by and large. And so I see it as a duty for the VLBI community to try and find spins of low luminosity active galactic nuclei to fill out this big missing chunk of spin measurements from the quiet majority in the radio universe. So if we're going to measure something like spin with a technique like very long baseline interferometry, and we're going to understand how to do this, we first need to understand how to do interferometry. And it turns out there's no better way to learn how to do interferometry than from watching ducks in a pond. So this is a fan favorite introduction to the technique. So here we're going to look at, I think, 13 ducks in a pond splashing around, sort of chaotically sort of flapping in the middle. But as you look at the far field limit, towards the edges of the pond, you see these smooth plane wave expansions. And our job as interferometers is to sit around the edge of the pond and dip our fingers at the edge and feel the lapping of water against our fingers and trying to piece together from that measurement the spatial distribution of ducks in the center of the pond. It's tricky, as you might imagine. So I'm stealing some beautiful animations from Michael here, which I imagine were somehow done in Mathematica. And so we're going to consider two spatial distributions of ducks. On the left, we have ducks that are very close together, and on the right, we have ducks that are rather far apart. And with each duck, we're just going to slosh it up and down And what I want you to pay attention to is the very edge of the pond. Look at the coherence length of splashing at the edge as these slosh around. And what you'll see emerge is that on the left, where our ducts are close together, when the spatial distribution is small, the correlation length is large. Or coherence length, rather. And on the right, when these ducts are far apart, the corresponding coherence length is small. And so this is a classic Fourier conjugacy relation, where the amplitude of this rippling, or these waves that we see at the edge, are telling us something about how many ducts are splashing and how frenetically they're splashing and how hard they're paddling, however you want to phrase it. And the coherence length is telling us about the spatial distribution. So it's an amplitude as a function of coherence length that is encoding the structure at the center of the pond. And it turns out VLBI is basically the same problem. So in this animation, you're seeing the Earth rotate with telescopes that are fixed at particular positions. So in this analogy, we can no longer change the spacing of our fingers. They are fixed in place, but the Earth itself is rotating our fingers, our telescopes, in a technique called Earth rotation Fourier synthesis. And that is sampling distinct coherence lengths for each pair of telescopes. And what you end up with at the end of the day is particular telescope spacings corresponding to individual measurements of Fourier components of the image. So really what we're probing is a Fourier transform of the spatial distribution of ducts, or in our case, light. And once you understand this at any sort of intuitive level, you already have all the tools you need to understand virtually all of the core results of my thesis. We're going to be working with this kind of data, trying to understand, hopefully, fundamental physical properties of these systems. And so 15 minutes in, here's the outline drop. I'll begin with a little bit of background on what I consider to be the most exciting physical feature of these systems, the black hole photon ring, which is a feature of strong lensing in an optically thin accretion flow around a black hole. And then we'll transition to spirals of polarization, sort of the nitty-gritty, what do you do with an actual image, and what can you say about the system once you have such an image of an optically thin accretion flow. And then I'll end with a brief discussion of how these sort of phenomenological analyses of images of these flows, how we can make these rich features emergent from a Bayesian inference pipeline for analyzing VLBI data. So to begin with, the photon ring. It shouldn't surprise you that black holes lens light around them. And because of this lensing, if you have a disk of emission on your image, on your CCD, on your telescope array, you will see sharp rings of light. And so in this picture, the disk of emission on the left is this beige disk, and on the right it is this green plane slice. So this is a cross-section viewed from the edge. And there are two paradigms that I find helpful for thinking about this problem. On the left, there's the forwards picture, where any point in space has an infinite number of light paths connecting to the observer. And these paths correspond to increasing numbers of windings around the black hole. And we index these windings by a number n. And this number n is going to come up again and again in this talk, so do try to understand. So this n is counting the number of half orbits that light is making on its way from an emitter to an observer. So in this blue trajectory on the left, there's light emitted backwards from this big orange ball, some little parcel of plasma. And it half orbits behind the black hole and then comes and hits us in the eye. Whereas this green trajectory is emitted initially towards us, but it's pointed just closely enough to the black hole that it's actually going to get whipped around once. Now it's going away from us, whipped around again, and now it comes towards us, n equals 2 in green. Whereas in the backwards picture, this counting falls a little differently. A point on the observer image, so you can think of this as a single pixel in our CCD, or just an image. A single pixel corresponds to a single photon trajectory, which we can trace back in time. And indeed, this is how most of the ray tracing codes that we work with in the HT function. They ray trace backwards from the observer image into the accretion flow. And this trajectory might intersect a plane around the black hole any number of times. And so I want you to look first at this geodesic on the very top of the image, which we're going to launch with a large impact parameter. And so this is going to zip past the black hole. It's going to be weakly lensed. And so it just sort of skims the accretion flow. It has one intersection with the midline. So this is in the n equals 0 image, but has no support in these higher n images. Whereas as we launch our geodesics closer and closer to the black hole, we see near orbiting trajectories. Suddenly, as we approach an image feature called the critical curve, the photons that we're receiving have gone on a rather tortuous journey around the black hole, zipping around multiple times, indeed exponentially many times, the closer we get to this critical curve feature. And the result of this is that when we look at optically thin accretion flows, we see infinitely many images stacked on top of each other. And so as we count up this half-orbital winding number n, we get exponentially radially demagnified images of the entire accretion flow stacking up on top of each other, to the point that they're nearly invisible on this projector. And so this structure, which is already very well approximated by the n=1 ring, this critical curve, to which the photon ring is always asymptotically approaching as these geodesics wind and wind, is very exciting to an observer. For two reasons. One, you can see photons orbit an object. This has not been done. And two, you can measure properties of the black hole which shape this photon ring. This is an achromatic feature given purely by space-time parameters like the mass of the black hole, the spin, and the inclination with which we view the system. And so you have a direct probe of the space-time if you can convince yourself you've seen this and you can constrain its shape, its size. And so it's terribly exciting. But why bother worrying about this? I mean, look, it's thin, it's dim. Well, in the simulations that we think are the best fit to Messier 87, we can just break down our images into the direct and indirect component, into the n=0 and the n=1, into the weakly lensed and the strongly lensed. And we can just look at how much signal we get as we march our fingers apart at the edge of the pond. And when we get to 8 gigalambda, when we're putting 8 billion 1.3 millimeter wavelengths between our telescopes, which is the longest we can get with the EHT's 2017 sampling, that's right about here. And so I've got the direct image in red, the indirect image in blue. They're comparable. So we're not resolving the thickness of this n=1 ring, but we are resolving its diameter. And gosh darn it, it's bright enough that it's about half our signal. And so even if we can't strongly constrain its parameters, we ought to be ready for it to be present, because it's shockingly bright in many of our simulations. So everything I've shown you so far applies to total intensity, but it turns out the photon ring is also very rich in polarization, so we're going to digress for a moment to talk about polarization spirals, and then we'll return to the photon ring. And along the way, we'll talk about how we understood M87. So to do this, we first need to discuss a little bit of zoology in the world of radiatively inefficient accretion flows. We usually bin the two varieties of accretion flows that we expect in these low luminosity AGN into two varieties. There's standard normal evolution, which has fairly weak magnetic fields that tend to go with the flow, and the overall picture you should have for sane flows is water draining down a kitchen sink, sort of smooth toroidal evolution across all radii, to a decent approximation. Whereas in the magnetically arrested disk case, there's a buildup of magnetic fields in the inner accretion flow, such that the magnetic pressure is strong enough to balance the infalling gas pressure. And so the gas couldn't smoothly infall if it wanted to. It has to sort of fight its way through the magnetic field, and you get a more variable, chunky accretion. And so it's very interesting to tell these two things apart, because as I hinted at earlier, the mechanisms for extracting rotational energy from a black hole and into these long, powerful jets is intimately tied to the magnetic field geometry very near the horizon. And these predict drastically different geometries and strengths of magnetic fields in that very space, in the ergosphere for spinning black holes. And what's also very exciting is that sanes become mad over time. As they drain from a consistent source of magnetic field and pile up magnetic flux on the horizon, they pick out a preferred geometry for the magnetic field given enough time. And so if we can look at a black hole and tell whether it's sane or mad, we're learning something about the history of the hole and how it launches any outflows we might see from it. And the problem is that at EHT resolution, we can't tell the difference. They all look like blurry rings. Very exciting blurry rings. We learn a lot from these blurry rings, but blurry rings nonetheless. And here, just making a point, we're altering virtually everything about these three simulations at the top row of this plot, and they all look almost identical in this particular snapshot to the eyes of the EHT, which are fairly blurry, even though they're 20 micro-arcsecond resolution, you know, size of an atom held at arm's length. A little too blurry for this kind of work. And so we need a new tool, and thankfully we have a new tool given to us by the fact that most of the light we receive is synchrotron emission, which is innately polarized perpendicularly to the magnetic field as projected onto the screen. So here I've taken that diagram from the previous plot from Ramesh's beautiful paper, rotated this to roughly the M87 viewing inclination, as we see from an eyeball on the right, and we're measuring, with polarization, some notion of the magnetic field projected onto our screen after modification by propagation effects like lensing and Faraday rotation and conversion and so forth. But in the simplest picture, we have a direct handle on the underlying magnetic field, because in a little patch of plasma threaded by some magnetic field, I'll use my arm here, this magnetic field, a little electron in this vicinity is going to end up on a helical trajectory around this magnetic field. And so that helical trajectory has a centripetal acceleration associated with it, and accelerating charges radiate. And that radiation is predominantly in the plane of that acceleration. And so the plasma itself is telling us the geometry of the magnetic fields through polarization, but it's a messy problem because of all these propagation effects. But in principle, we have a handle on telling the difference between MADS and SANES because they ought to have intrinsically different magnetic field geometries. And that is precisely what we set out to do in this paper with my beloved colleagues, George Wong and Ben Prather, and Ben Prather's in the audience. Hi, Ben. And I especially want to send a general thank you to the Illinois group under Charles Gammey, which does a tremendous amount of work in running and maintaining GRMHD simulations like these for use in EHT and EHT-adjacent work. And we set out to look at this library of simulations and try to tell the difference quantitatively between magnetically arrested disks and standard normal evolving disks in the context of M87 observations. And recall that M87, we think we're looking at it nearly face on. You can imagine we're looking down at a spinning top. And so there's a potential translation of an axisymmetry in the black hole accretion system to a rotational symmetry on the sky. And if you just look naively at the blurred picture, so blurred to EHT resolution, of the polarization we see from these two example snapshots, you see a very different picture for the polarization. In the MAD, we see this nice coherent spiral. In the SANE, it looks almost like a starburst. Now, if we think back to our picture for the magnetic fields and the fluid velocities in these models, this already makes some sense. In the SANE picture, it's this nice, smooth toroidal infall. That plasma is dragging a magnetic field behind it, and we're looking perpendicular to that magnetic field. So if we think the magnetic field is a nice, smooth circle, then the polarization, 90 degrees off, ought to look something like this radial starburst. Whereas in the MAD, where there's presumably stronger radial and vertical component to the magnetic field, that can contribute non-radial polarization. And so we end up with a more general family of spiral polarizations. But we want to make this quantitative. We don't want to just squint at these. And so we set out to do essentially the simplest possible thing, given that observation, which is take a Fourier transform with respect to phi. We love Fourier transforms. We can't help ourselves. And so we break this down into basis functions, which are diagrammed on the right, which basically just capture different evolutions of polarization with respect to azimuthal angle in the image. And we a priori expect that this m equals 2 mode, this beta 2 mode, which you might have heard from various EHT polarization talks in the past, ought to encode what we care about most because of this inherited symmetry. We're inheriting the axisymmetry of the underlying system because we're looking face on, and it becomes a rotational symmetry in the image. And you might be jumping out of your seat saying, oh, it's just E and B. It is just E and B when you break down beta 2. As this real part, which contains radial structure or circular structure, and the imaginary part of this coefficient is just handed spirals. So it's precisely E and B, sort of radially averaged. And when you plot this vast library of simulations, just according to this coefficient and color by spin, which we weren't even really hunting for in this paper at first. We were looking mostly for MAD versus SANE, but when you color by spin, you see a breakdown. You see the colors begin to separate. And that's tremendously exciting because we otherwise have basically no handle on this parameter. And it turns out there's a deep reason for this that I'll discuss in a moment. But the observational picture here is if you can get a sense of what the quiescent or really just an average polarization structure is like for a source, suddenly you have a handle on the spin because you are looking at emission predominantly from the ergosphere, where the spin of the black hole is really doing the work, setting the tune for the rest of the accretion flow. Now, when you color by Mad or Sane, and this diagram is taken from EHT paper 8 on M87, so the theoretical analysis of the polarization images, you see something very exciting, which is that the range of these values permitted by EHT reconstructions of M87 strongly disfavors this dark orange, which is rather invisible on this in this lighting, but which are otherwise extraordinarily good at mimicking every other tool we have, every other metric we have for comparison to our images. So these retrogradely accreting sanes, and by retrograde accretion here, I just mean our black holes spinning one way, but the large-scale accretion flow is spinning the other way, which is not too crazy if you think of, say maybe a recent merger, which could create some torn disks on a galactic scale. And so maybe when we happen to look, we might be looking at something retrograde. But these are forbidden by this range, and so we're only left with MADs. And so this is critical to the conclusion by the EHT that Messier 87 hosts a magnetically arrested disk. It's coming from this azimuthal variation of polarization. And so the crucial takeaway here, looking forward, in my opinion, is that spin reveals itself in polarization due to a particular sort of causal flow chart. So the black hole spin drags the spacetime. The spacetime tells matter how to move, so that it's effectively dragging the plasma along with it. The plasma is dragging its own magnetic field, it's frozen in, carries it behind it, and the magnetic field is revealed to us by polarization. And so by running the logic backwards, we build sensitivity to spin from polarization. And this sort of takeaway is the most important piece you could take from this entire talk. I want to especially highlight a few papers. So Razia Mami and Andrew Shale have both done excellent work sort of related to this, but I think most importantly, they've looked into where light is coming from in these accretion flows and generally found some support for this conclusion that light is predominantly coming from where frame dragging is most important, so in this ergosphere. And I also want to highlight papers by Sean Ressler and He Jia, which have tried drastically different GRMHD schemes. So these are all sort of torus-fed, I say bog standard. Bogs are great, it's not an insult. But Sean Ressler's work uses stellar winds to feed the Sagittarius star accretion flow. He Jia was testing various sort of Bondi accretion, rotating Bondi accretion, sort of wacky scenarios relative to these nice simple tori. And they get vastly different Stokes I variability, so total intensity variability. But the picture for the quiescent polarization, the average of the polarization, seems to be similar. And so there's some convergence happening in the wide world of GRMHD around this kind of inference, which I find very exciting. So I promised photon rings would return. So there's an opportunity for a mental exercise here. If you have a napkin that isn't completely covered in orange creamsicle icing from your cruller, if you just draw a rough diagram of this or of maybe 2 or 3 ticks, and we don't have too much time, and you flip it upside down. So if you mentally flip this diagram of these beta 2 coefficient phases, what you will see is that the radial mode, so the real part, is unchanged. Radial continues looking radial, circular continues looking circular, but the imaginary part appears to flip. The handedness is flipped. This is a complex conjugation of beta 2. You can think of this as just a negation of the B mode. And this very simple picture I see as a nice motivation for what photons in the n equals 1 subimage see. So photons which are initially emitted away from us in the Messier 87 accretion flow, which then loop around behind the black hole and then come and hit us in the face, are basically seeing the underside of the magnetic field structure. They're seeing a flip in some sense. And it turns out this is a shockingly good prediction for the simplest sort of zero inclination, zero spin, high end limit of a much more general symmetry, discovered by my amazing colleague Mina Himwich, who's in the audience, of the Penrose-Walker constant. So this constant encodes both the magnetic field structure and the curvature of space-time in an elegant way, which sort of captures all of the polarization information in synchrotron emission very elegantly, especially for axisymmetric emission. And this constant complex conjugates as you look at emitters on opposite sides of the black hole, corresponding to increasing numbers of subimages. And it turns out this is a booming signature in polarization in our simulations, particularly magnetically arrested disks, which are now favored not just for M87, but also for Sgr A by the Stokes I analysis by the EHT. And so this slide summarizes what I see as the gold mine that is polarization, where as we crank up the spin of the black hole, and remember that causal flow chart, it's dragging the plasma is dragging the magnetic field, which is, we see in polarization, we see that the polarization becomes more radial either direction. As we crank up spin, either in a prograde flow, where the large-scale accretion flow agrees with the central black hole, or in the opposite case, where they disagree, we're always looking at 230 gigahertz, it seems, at the very innermost scales, where spin is important. It's setting the tune, and we can see that tune being played out. And yet in the photon ring, this reverses. We see a reversal of the handedness. This is an intrinsic difference between the direct and strongly lensed emission. And so it's something we can look for with an interferometer, which is innately good at separating spatial scales like these. And I just want to highlight there's a whole cottage industry of fellow polarization obsessives who have been helping to sort of build the language for talking about and thinking about these flows. And so I also want to highlight that there's a simple VLBI picture for targeting this reversal. And I'm going to motivate this in the worst possible way, which is via sideways ducks. So if you imagine your fingers are close together at the edge of the pond and you feel sloshing up and down, you're seeing the direct image in polarization. But if you put your fingers far enough apart, you suddenly feel correlated sloshing side to side. There's an intrinsic difference in the polarization of the sloshing that you feel once you stretch your arms apart far enough. That scheme basically works for detecting whether or not an individual measurement is dominated by the photon ring or not. Polarization is helping us know whether we're really seeing the photon ring. So just in my last few minutes, I want to motivate the sort of general conclusions of this thesis using some semi-analytic model fits with this simple model I've built in the last couple of years of my PhD. So why bother with all these complicated simulations? Why bother with imaging or geometric model fitting if you could just fit the accretion system itself? So fitting something simple and geometric, but not on the sky, but in the space-time, in Boyer-Lindquist coordinates, in the language that the black hole uses to describe its environment. And this has the nice benefit that you can simultaneously fit things like the black hole mass, or spin, or inclination, along with things like fluid velocities, or electron temperature distributions in principle, or just something like the peak emission radius, something we normally have to constrain from simulations. And this is motivated in part by looking at blurry donuts, which have no intrinsic physical scale. You can't look at this image and a priori declare a mass without some notion of what the heck the plasma is doing. I can always hand you an adversarial distribution of plasma densities and temperatures, which could deceive you about the imprints of the space-time. And so my answer to this is a code called KERBAM, Kerr-Bayesian accretion modeling. It's meant to sound punchy and exciting. Which aims to make a bunch of assumptions to make this problem as simple as possible and as fast as possible. So it's an axisymmetric one-zone model for virtually everything about the plasma, purely equatorial. It aligns the disk spin and the black hole spin. It's a very simple spectral behavior, and we're only going to fit Stokes I for now. So while I've just been telling you all about polarization, for now we're just going to stick with total intensity. And the result of all of this is that you can get posteriors to all of these exciting physical parameters like mass and spin in a matter of hours on a personal computer. And the picture here is basically we disentangle all of the space-time and viewing parameters on the right from all of the fluid parameters on the left. So on the left, we're going to encode things like the typical emission radius, the axisymmetric fluid velocity or magnetic field orientation, and so forth. And on the right, we can shrink and scale or spin up the black hole. And together, these specify everything about the image. And so this already has a pedagogical purpose, in that we can break down the images we see, not just into n equals 0 or n equals 1, but into the individual components of the image that contribute structure around the ring. And we can see already synchrotron emissivity and the combined sort of Doppler and gravitational redshift are sort of entering its similar order. It's not so straightforward to interpret a brightness asymmetry as just a Doppler boosting peak. And so this is all very useful. It's also very nice to investigate photon ring properties. I was already talking about these polarization flips as you increase n from 0 to 1 to 2, et cetera. You see it dance back and forth. You can see this in these model images, which you can evaluate. These are 4K images of an accretion flow. It takes about 1/10 of a second. And I would say this is the fastest in the business, were it not for my amazing colleague Dominic Chang, who has since expanded this code to arbitrary off-equatorial geometries, rewrote the whole thing in Julia, mounted it on GPUs. It's 1,000 times faster now, but what's a factor of 1,000 between friends? I mean, who's counting? Basically comparable. Dominic's work is extremely exciting and will revolutionize how we think about black hole images. But this is just another pedagogical usage of this code. But you can also fit data with it, and here's a fit to the M87 2017 data from EHT. And so I'm not using very strong priors here. I'm not using the GRMHD simulations to inform a prior. I'm basically letting everything float. And what I find are very wide, unconstrained posteriors characterized by a handful of modes. And it brings me no end of delight to see that there is basically one mode per distinct mass measurement from some other technique, regardless of their disagreement. So this is, in a sense, the most politically correct posterior you could ever publish on something like the M87 mass, because everyone gets their little consistent blob. But what I find most useful about these posteriors is that you can, after the fact, think about what regions of parameter space you trust. And of course, these things can also manifest as priors. You could say, oh, we really shouldn't let the typical optical depth in the plane exceed 1. I mean, come on, there's lots of other good reasons to believe it's optically thin. But in general, you see these big degeneracies. You can scale your black hole in, but scale your emission farther from the black hole, and you get a similar ring size, that kind of thing. And so I see this as a general sort of reason to search for trustworthy plasma priors. The profound statements you can make about these systems in the absence of plasma priors are very limited. And so I consider this a motivation for what I see as the conclusions of my thesis. So zooming out, where are we? What comes next? Optically thin accretion flows reveal a great wealth of information in polarization. This is very clear from all of the EHT-adjacent work that I and many other authors have pursued over the last few years. Polarization is vastly richer than total intensity because magnetic fields are so important to understanding these flows. And we know what to look for. We have tools to explore these systems in the terms that are most important for setting their behavior, for setting their outflow characteristics. We can think about their magnetic field geometries and see the effect that has on images in natural ways. So we're learning how to talk and think like these black holes. And M87 and Sgr A will be a testing ground for complementary methods. I see this beta 2 sort of decomposition with these polarization spirals as step 1. We will have all the time in the world to think of more nuanced tools for understanding these systems that we will be observing for the rest of time. And if we start to see consistent answers from all of our tools, especially around spin, I think we have a duty to extrapolate. And so I'm very excited about demographic applications of polarization work. And there's some really exciting and sort of foundational studies here by Don Pesci, which try to sort of synthesize all that we know about low luminosity AGN into a realistic pitch for VLBI surveys of things like mass and spin. And here, just in broad strokes, motivation. Oh, these are really wiggling. How fun. So this part isn't a movie. So here, this diagram is just showing what happens to the polarization, again, as you crank up the spin, which is just a number between 0 and 1 for a given black hole mass. And as we crank up the spin, the polarization becomes much more radial. And what I want to point out is that this feature is much larger than the EHT resolution. You don't need to resolve the event horizon with 2 pixels across it to really get some sense of this. And so that's what this blurring is intended to convey, is that some sense of this polarized structure persists even when you're only marginally resolving your source. And so potentially we could learn a great deal about low luminosity AGN by looking for scarcely glimpsed rings of polarization when the viewing geometry and the optical depth permits it. And we're only just getting to know the event horizons of M87 and Sgr A, and yet they've already surprised us. All of these conclusions are based on a relatively small family of GRMHD, and so we should be willing to see challenges to this paradigm. Because as these simulations improve, these techniques will improve in lockstep. There's a bit of a variability crisis, for example, in Sgr in our comparison to GRMHT models of the accretion flow. Sgr seems less variable than we think. That challenges the way we do our simulations, and yet there might be some harmonization around quiescent polarization. And so as we learn more about these sources, we will learn more about every source in principle. And so my conclusion, I feel like I'm paraphrasing a tea towel from across the Midwestern US of sort of bless this mess kind of thing, but that really is how I come away from this PhD, is that the accretion theorists have a lot to say here. There's a big role for accretion in quests for physical properties of the black holes that are most important to us. So embrace the mess, and I'll take questions. Thank you.
Okay, questions for Daniel?
Don't be shy. Charlie, sorry.
Great talk, by the way. Tell me more about this variability crisis.
Sure. So in very simple terms, our GRMHD are wildly varying, and Sgr is not, 230 gigahertz at least. And so when we compare our models to Sgr by lots of different metrics, like sort of the angular size that we perceive when we fit with VLBI, we're much better at getting that right with the tools we already have than we are at getting the variability right. And so this points to things that we're currently ignoring in our GRMHD that we could do better. You know, sprinkling something like viscosity or resistivity or sort of your favorite way of improving GRMHD. From a recent paper by Lena Mitrikova, actually, who's also in the audience, looked at this in the context of Stokes-I light curves and found that these wind-fed models that Sean Ressler is working on, Sean Ressler and friends, are typically a better fit to the overall sort of structure of variability in Sgr than most of these torus-fed GRMHD. So my guess is that this is something we'll understand much better in the next couple of years, because there's a lot of progress already.
Thinking of the answer to this, do you ever expect to see anything in circular polarization?
Yes, circular polarization is incredibly rich, and it actually has a lot of the same symmetries, or at least sort of analogous symmetries, especially in the photon ring. But Stokes V is a little bit more complicated because it can be sourced by what I would consider less intuitive schemes. I find it a little difficult, at least, to make sense of Faraday conversion in the context of lensing symmetries. It's very dependent on the plasma. Our local expert is Angelo Ricarte, who's done some sort of seminal work in trying to understand resolved Stokes V in these sources. Yeah, it's very rich. Floor.
Yeah, so I noticed like the EHD are also trying to like build extra telescopes to like help with the VLBI. So like how would that help with the polarization?
Yeah, so basically in two ways. I think the big boost that more dishes will bring to the NGHT is in spatial dynamic range. So at the moment we reconstruct these very compact fields of view where we're maybe 2 or 3 or 4 maybe on a good day horizons across. But with better spatial dynamic range that comes from more dense sampling of the Fourier plane rather than much longer baselines, you start to pick up the jet. And so there are huge sort of gains to be made in understanding the magnetic field structure of the jet right as it's being launched from the inner accretion flow that will help disentangle a lot of what I see as the big unknowns, especially in hunts for sort of understanding whether BZ is actually happening with Blandford-Znayak energy extraction. It's all very complicated, and it'll be hopefully much simpler once we see the jet. Yeah. Yuri.
Thank you. I would like to follow up on the question before, although I will try to make it more painful to you.
Perfect.
So it looks like I'm this theorist. I'm telling to you, what you should expect. And right now I will, step back a little bit, and now you guys are welcome to use all the tools which I have developed to actually study accretion flow in M87, Sgr, and other sources. So there is a high chance that you will become a doctor today. There is, and you will have something like 40 years in front of you, about 40 years until you retire. So my question is, can you please, I mean, you understand not only the theory very well, but also the current state of experiment, what is planned for the future. So I would like to ask you to try to risk and predict what will happen in the next years before you retire in terms of using these methods to directly through Stokes' eye, or indirectly, if you allow me to say it like that, through polarization, detecting and using N1, N2 rings to study properties of these systems. Will this happen for Sgr A? Yes, no. Will this happen for M87? Yes, no. For how many more sources? So your prediction then will come back to that 40 years later.
Okay, so this is an excellent question. I love to be far-reaching where possible because it means I get to put on a theorist hat and not worry about how good detectors are in 40 years. They'll be great, you know. So I guess what I would say is you can break this down by sub-image index n for what kind of science you want to do and how agnostic it will be about the accretion flow. So if you restrict to n equals 0, so just direct images, then I think there's a lot of potential use where the arrays of the future might involve very disparate baseline lengths. You might have one orbiter in space acting as a very long arm of an interferometer at something like 230 or 345 gigahertz, in which case there's a large number of AGN where you will probably be optically thin, and you might be able to see down to the horizon, but you're never going to make an image. You don't have imaging quality data. So you get one baseline, probably a poorly calibrated baseline, where you might not ever have any hope of any sort of phase information, but you get polarization on one baseline. And so what I laid out in a chapter that I didn't have time to discuss is a way to maybe use this scenario, a single baseline, to measure under GRMHD assumptions something like the quiescent polarization spiral pattern. And if you believe a given set of simulations, that just is a spin measurement with some fairly large uncertainty. Now, with that same very long baseline, or extremely long baseline, if you will, you can also do detailed studies of lensed images in sources that are closer, things like Messier 87 and Sgr A. And to comment on Sgr A in particular, looking into this in the context of polarization, my guess is that you will probably not get the photon ring at Sgr A at 230 at any baseline length, because there's just this mixing of scales inflicted by interstellar scattering that prevents you from ever being dominated by the photon ring at 230, though this should be quadruple checked, but that's my instinct. At 345, if you're off-axis, you might have some hope. Off-axis from the scattering kernel, I've at least seen simulations where it happens to work out okay at 345, but probably you need to go higher. And it helps because Sgr is much brighter than M87. So these higher frequencies that are more sensitivity dependent are trickier. I could also spend about 40 minutes answering this question. So I guess what I would say is, for many other sources besides M87 and Sgr, I think doing sub-image science is very, very hard. But for M87 and Sgr, it's doable, and it will probably work in both sources if you go to a high enough frequency. Does that make sense? Good. Maybe one more question? Go for it.
345 the highest frequency that you're considering there, or you think you would go like higher?
Well, I'm so bold as to have a plot in my thesis going as high as 690 gigahertz, much to the chagrin of every engineer I know. What I would say is that the higher frequency you go, the more optically thin these sources become, and it turns out the higher the relative or higher the ratio between the n equals 1 flux and the n equals 0. And my hunch is that this is largely an optical depth effect. You're pushing the Eddington-Barbier surface deeper and deeper along geodesics. The higher frequency, the better. The problem is that it's very difficult to build an instrument sensitive enough to get detections at those high frequencies for a source as relatively dim as M87. But yeah, when I put on my theorist hat, I'll consider terahertz. Why not? Sure.
I think we should close right at the hour.
Sure.
This concludes the public portion of the defense, and let's thank Daniel again for your talk.
I just want to add, so for those who aren't about to go to the private grill session, everyone else should go to Floor's celebration for her successful defense this morning. So congratulations again, Floor. Yeah.